Okay, so we are finished about chapter 1 WDM overview. Let's continue with the second chapter's transmission media, which is fiber. Okay, so actually we have a lot of different fiber. Different fiber can use for different distance, has different features. Let's know them. Okay. Before we know the fiber, so let's check the optical fiber structures. Okay, actually, our fiber has three different parts. The fiber core, which is made by the glasses. Okay, and another part is collecting, which is working with your fiber core to make your light transmit in the fiber core. Okay, because they are glasses. If the light transmitted in the glasses, it can transmit a very long distance. Okay, if we outlet to pull to the collecting, the light will disappear very quickly. Okay, the last part is coding, is used to protect your fiber, so let's see how does our light transmit in the fiber core. Before we know that, we have a basic knowledge we should know. Check this out. The light can be transmitted from air to glass very easily because the air diffraction index almost 1. The glass is almost 105. That means the diffraction index air is smaller than the glass. So when the light transmits from the media, reflection index is lower to the media which reflection index is higher, is very easily to transmit into it. But we will have two different things. That is, first of all, we call reflection will have it. But for this one, the incidence angle theta 1 is must 100% equal to the reflection angle theta 3. So this two part is equal. Okay, but for the reflection is a little different because the reflection index is larger in the glass. So the reflection angle theta 2 must be smaller than the incident angle theta 1. Okay, so that's the knowledge we should know. But our light can transmit in bidirectional. So actually, so what happened if the light transmit from the glass to the air? What will happen? Okay, so if the light transmits from the glass to the air, I think the first go like this way. So first of all, this place you will have a reflection we have there. But for the incident angle here, I think it must be equal to the reflection angle over here. Okay, but another thing will happen, that is a reflection, because the reflection index of the air is smaller. So over here, reflection angle, this part must be larger than this one. Okay, this one is larger than this one. If we control this incident angle over here from the glass to the air, this is the angle over here. If we control it, I think this one may be equal to 90 degrees. So another thing will be happen. Check this out. When we control this angle over here, because in the air the reflection index is larger. So when it equal to 90 degrees, this one must be smaller than 90 degrees. Okay, so all the light will be like this way. Then that means no light will be reflection. All the light will have the reflection over here. So at this time, we call it total reflection of the light. So that's what we want. We want our light always transmit in the glasses, not output to other parts. Actually, in your fiber, the fiber core is this part. This part is collecting. So if you want to have total reflection in your fibers, I think the collecting reflection index should be smaller than the reflection index of the glass, right? For example, this is 1.5. This one should be 1.1 or 1.2, right? So at this time, we can have the total reflection. The light will be always be limited in this glass area. So this way, your light will be always transmit in this form. But when we have this total reflection, another thing will be happening. That is, if we change the angle of this one, of the incident light, so this transmit routers will be changed. Okay, if the fiber is very long, when we change the angle a little, the distance will be changed. And this time, maybe your light will have some delay because the distance change. You need more time to transmit from source to sink, right? At this time, you will have this delay. This delay, we give it a name we call mode dispersion. Mode dispersion. We have this mode dispersion is because this input angle can be easily changed. So I thought, so this fiber we give the name we call multi-mode fiber. If the light can transmit in different angle in this fiber, we call it multi-mode fiber. Okay, and it cannot used for long distance transmission because you will have mode dispersion problems, make your signal have bit error. And this time, I think so we will limit it the error of this glass, okay, and make it become very small, and that will limit it. The light can only transmit like this way in this fiber core. So no matter the angle cannot be changed anymore. So the delay problems, we don't have it anymore. So we will never have any mode dispersion for this fiber. This fiber will give it a name we call single mode fiber. So actually, single mode fiber can transmit to hundreds, thousands kilometers, but a multi-mode fiber can only used for less than 2 kilometers. Actually, in our network, this one is, and this one we like to use for the interconnection. Interconnection. Okay, this one will be used for long distance communication, such as WDM or other transmission network. Always like to use the single mode fiber. Okay, the single mode fiber. And about the fiber, we already know what is single mode, what is multi-mode. Actually, our fiber has two characteristics. The first one is attenuation. No matter which fiber you buy, they must have attenuation. But the attenuation features, we should learn it clearly. That is, different wavelengths transmit in the same fiber will have different attenuation coefficient. You can check this picture. In this picture here, is we call it 3010 nanometers error. Here we call it 5050 nanometers error. Also we like to call it C band and O band. This error you can check. This error the attenuation is very low, right? So at this time, if you want long distance transmission, I always want lower attenuation, right? So our single mode fiber will use 3010 nanometers and 5050 error nanometers to transmit our signals. Okay? But actually, our WDM network, our DWDM network only used 5050 nanometers. There are reason. First reason is in 5050 you can check the attenuation coefficient here is much smaller than 3010. It's much so this wavelength is much better for longer distance transmission. All right. So actually, in 3010 nanometer error, the dispersion coefficient is almost 0.3 to 0.4 dB per kilometer. But in 5050, the attenuation coefficient is almost 0.17 to 0.25 dB per kilometer. That's the first reason, but it's not the real reason. The first reason is major reason or the real reason. That is our very important unit amplifier, optical amplifier, can only amplify the wavelengths in 5050 nanometers. So that's why our DWDM only use 5050. Okay, so that's the attenuation over here. You can check over here. We have another multi-mode wavelengths. You can see multi-mode fiber will use this wavelengths. And because for the multi-mode fiber, the distance is only 2 kilometers, so the attenuation is a little higher. Doesn't matter. You don't care, right? Because it's not for long distance transmission. It doesn't care about the attenuation. If just not too high, right, will be acceptable, right? Another features that is dispersion. Dispersion. We already introduced one of the dispersion that is mode dispersion. Okay, we have another dispersion we call chromatic dispersion. You can check this picture to see, for example, in the south station, I want to send 3 bits to sink station. These 3 bits may be 1, 0, 1. But in optical layer, how do we mention the 1, 0, 1? We can use optical plus to mention 1, 0, 1. For example, if we have plus, means 1. If we know plus, 0. So 1, 0, 1 can be transmitted like this way, right? So if the sync station receives this plus, it will detect the 1 by 1. 1 plus, that is 1. No plus, 0. 1 plus, that is 1. So I can transmit 1, 0, 1, this kind of information from source to sink by this optical plus, right? So like this way. But this plus, our optical source is not very stable, not very, very stable. Actually, when we launch this plus from source to sink, this part, and this part, the frequency is a little different with this central frequency. Its highest part, we call it central frequency. It's a little different with central frequency. Also has the same problem in this plus. So one thing that is different frequency will be transmit in the same media has different speed. So after long distance transmission, because the frequency is a little different, so this part may be running faster. This part it will be running slower. So after long distance transmission, it will be like this way. This part maybe will catch another pulse. But don't worry, in my sync station, when I got to the signals, we will have one line. Actually, the power we detected higher than this line, we consider is 1. Lower than this line, we consider 0. So for this time, it can still be detected as 1, 0, 1. No any bit error we have. But after the long distance transmission, the two pulses may be catch each other. Will be like this way. At this time, when I receive it, when I got this power, I may detect it as 1, this part, because they catch each other, the power already become high. It will become 1, 1, 1, right? So will 1 bit error will be have. So that is chromatic dispersion. We will have some bit error because these problems, some one running faster, some frequency running slower, right? So uh, so if we have these problems, how do we fix it? It will affect our service quality, make our have error